Hello, everybody. Thanks, Hexa-X, for this wonderful workshop, and thanks for the invitation. So I will go directly just to make it on time with a presentation from the TERRAMETA side. I'm G.Alexandropoulos. I'm the project's technical coordinator, and we're going to actually overview the first year's activities of the project, target, of course, the questions raised by the workshop, where we will try to provide answers from our project's perspective. The presentation is going to be around the technology of reconfigurable intelligent surfaces, which is the core focus of this project. And actually, we will discuss the potential of this technology for THz wireless applications. You will see a very preliminary feasibility study that we have conducted within the project, as well as the open challenges. So in a nutshell, our project actually is focusing on the investigation of groundbreaking technologies for 6G, demonstrating the feasibility of ultra-high data rate wireless communications, leveraging terahertz metasurfaces. As I said before, this is the core technology within the project. So we're targeting, and we have been already working on novel high-performance terahertz hardware, including low power consumption wideband switches, RISs, and transmitters and receivers for the bands. Just for being totally clear here, you will see on the bottom of this slide, the definition that we have within the project about terahertz is the following. It goes from the terahertz from 100 gigs to 1 terahertz, although lower frequencies, these are the millimeter wave bands. Mainly in the project, we're focusing in terms of demonstrating technologies on the 140 gigahertz band and the 300 gigahertz band, as you will see later on. Apart from designing this terahertz hardware, we're also focusing on designing various terahertz components, advanced network analysis and optimization techniques for this, and of course, use cases related to the technology that we're actually working on. The TERRAMETA terahertz network will be driven by 6G usage scenarios and requirements, and actually we're focusing both in indoor, outdoor, and indoor to outdoor scenarios. Our demos are two actually, one on a real factory setting and the other on a telecom testing field, as I will describe later on. Here you see the pillars of the project, the design of terahertz components, the design of terahertz metasurfaces, the characterization and the modeling of those frequency bands, and of course the design of signal processing and network design algorithms incorporating the terahertz metasurfaces and the terahertz components like transceivers within the system. Going further, the consortium of the project. Here you see the partners. There is the project coordination by INS Tech in Portugal, the technical coordination by the University of Athens. You see also the expertise of the different partners. University of Herefordshire, which has expertise on reflect arrays and transmit arrays and beamforming algorithms. University of Oulu, which is actually working on designing terahertz antennas and measurement and integrated circuits design. The Institute of Telecommunications, again in Portugal, with expertise on the reflect arrays and transmit arrays, as well as antenna characterization. Intracom Telecom, which is actually working on the baseband unit necessary for our demos and with extensive expertise on signal processing. Sealeti, with expertise on reflect arrays and transmit arrays, this transmissive RIS technology that we'll discuss later on. University of Oulu, network design and optimization, metasurfaces. Dell Ireland on industrial operations and management, which is responsible for the real factory demonstration that we have. The University of Braunschweig in Germany on the terahertz characterization and propagation modeling, as well as the standardization activities. And SME, the ACST, working on terahertz transmitters and receiver design. The Nova University in Portugal, again, focusing on memristor design and fabrication, which is one of the technologies that we're focusing for realizing terahertz metasurfaces. And British Telecom, which is working on the system architecture and the exploitation of the application scenarios. I will discuss today the use cases and applications which are very relevant to a deliverable that has been already sent to the European Commission. You will see our advances in development up to now on the hardware perspective, on the channel modeling, signal processing, the planning of the proof of concept, which are in very good shape, and the standardization impact at the end. Here you see actually a list of the use cases and applications that we have been discussing and designing within TERRAMETA. And we have actually various application types focusing on the coverage extension, on the network interoperation, backhaul planning. Those frequencies are very relevant for backhaul. So this is definitely a use case that we have working on. High capacity connectivity to be able to confront with this huge amount of data being, especially if you consider a real factory scenario, being collected by various sensors. All this information needs to be transferred to data centers to take some decisions. And actually, to do that, we need those high capacity links. Localization and sensing, another application type, RF sensing and network resilience and multiple access. For use cases, just to mention a few, the blind spot coverage, as you see here, both for indoor and outdoor, we're going to consider mainly reflective RIS for do that, and the use cases where we have a blocked line of sight, hybrid indoor and outdoor repeater to do this coverage extension, again with reflective RIS, but we also considering transmissive RIS and RISs that are extremely flexible in terms of reconfiguration, backhaul planning, the backhaul and integrated access, high capacity connectivity, both short range, short haul and mid haul, with various forms of metasurfaces. Just to mention here that there are various technologies that we have been using and forms of metasurfaces. Apart from, let's say, the conventional, which are configurable reflections, we are also considering metasurfaces of fixed reflections, anomalous reflections, but fixed. This could be very relevant in certain scenarios and very easy to deploy with minimal overhead in coordinated with the network. Actually can be nearly zero. But apart from that, we're working on hybrid active and passive metasurfaces that are capable to do simultaneous tunable reflection and reception, but also we are considering the metasurfaces as a technology to realize extremely massive MIMO transceivers, meaning that using actually the metasurface panel to replace conventional antennas in order to realize either transmitters or receivers. Localization and sensing is actually an application type that we have been working a lot. And the use case, as you see here, it could be used for various terahertz, as you see here, RIS edit outdoor and indoor sensing, RIS edit multi-access sensing, various types of metasurfaces, and capability to actually detect multiple targets. For the RF sensing, we have the use cases of joint communication and sensing with dynamic metasurface antennas, environmental mapping and imaging, large-scale distributed sensing in a factory, enhancing throughput, localization, and mapping in factory settings, ANs, with various forms of metasurfaces. So going further, here you see on the left today a typical, let's say, list of the speculative KPIs and their requirements related to 6G. And on the right, you see KPIs and their requirements that we have concluded after working on the demos that we are planning for at the end of the project. And this mainly refers to this real factory scenario that we have in mind, where at the end of the day, what we want is to have robots producing huge amount of data using RISs and terahertz in order to forward all this data, even in cases where there is no line of sight to data centers for further processing and decision making. So those various manufacturing use cases may require additional KPIs with higher requirements. And here you see some values. The minimum bit rate to be of the order of 3 gigabits per second, minimum range 10 meters, the SNR around 5 dB, bandwidth localization approximately at 2 gigahertz, frequency band 140 and 3 gigs. These are the frequencies that we're focusing within TERRAMETA. Different modulation schemes, the bit error rate rather demanding to be less than 10 in the power of -9, the packet loss less than 1%, throughput around 2.8 gigabps per second, and end-to-end latency of less than 10 milliseconds, and the jitter less than 2 milliseconds. These are relevant to the scenarios that we are targeting to demonstrate at the end of the day. Now, let me proceed a little bit with actually a very basic feasibility study that we have decided to include in this presentation to get a feeling of what could be the characteristics of a metasurface in those targeted scenarios and frequency bands. So consider a scenario where there is a blocked line of sight between a transmitter and a receiver. Base station could be and a user. And consider that both the base station and the user are in the far field of an RIS on the bottom right, a basic sketch of this scenario. And assume that there is a distance link of 100 meters at 140 gigahertz, and there is an RIS placed at equal distances between those nodes. You see those distances D1 and D2 being at 50 meters. Also consider that the minimal detectable power of the user, this PRX, is minus 60 dB. So if we get this basic link budget formula that you see here, where you can see that we have the antenna gain being included, the transmit power of the base station, some typical values of the antenna gain, the base station, and the transmit power of 20 dBms. There is incident and output angles, let's assume, that are at 0 and 45 degrees respectively, and there is the antenna gain on the UE, we have assumed to be 10 dBi. So here, what we want to do in this study is to try to understand what should be the characteristics of the RIS. So in order to do this formula, we have included the RIS's radar cross-section, actually for typical radar theory, which is bounded by the specular reflection limit in a perfect electric conductor surface and can be estimated as a function of the aperture efficiency of the RIS, this eta with subscript AP, this aperture, according to the following expression, this expression 2 that you see here where my cursor is. Now, to meet the requirements set by this minimum detectable, this minus 60 dBm received power at the UE that we said before, we need to determine the aperture efficiency and then the RIS's aperture via this D parameter that you see there. So this aperture depends on many factors, including the phase quantization error, the unit cell insertion losses of the RIS, and for passive structures, it is expected that a reflect array can provide the 50% of aperture efficiency. Additionally, the integration of the reconfigurable technology will further degrade the performance of the metasurface, and actually based on the various technologies out there regarding that, we have considered at least 3 dB of insertion losses. Therefore, the aperture efficiency of 25% can be actually considered as a realistic upper bound number. So putting all this above together in the previous formula, we can conclude that the gain of this value that you see here, 18.32 dB, is actually missing, which means that the RIS is tasked, is mission to compensate. So the RIS role could be to compensate this gain. So if we use this value to solve this radar crossing actually section formula that for the aperture efficiency that provided before, this results to D being equal to 110 millimeters, which corresponds to an RIS that has in total 10,540 elements for this considered frequency, which is the 140 gigahertz. So in a way, this number provides a vivid picture of the scalability required for the RIS technology. And of course, in this size that you see, we have to pack all these elements, which is extremely challenging with the technologies up to now. And this is one of the main focuses of the TERRAMETA project, to try to provide feasible solutions for realizing in these frequencies metasurface. So having said that, we have been working on various layers on the metasurface design, apart of course, from the high power terahertz sources, which is something which we are working on. We're working on a scalability analysis of the RIS as a panel, both for transmissive RISs and transmissive RIS is an RIS where we illuminate from the one side and we have this refraction, tunable reflection from the other side, and the conventional, which are the reflective RISs. Frequencies are, as I said before, 140 and 300 gigahertz. So we're working on the design, integration, and characterization of the controlling units. This refers to the RIS panel. On the unit cell level, we have been actually working on design on the same frequencies to provide compatible switching technologies. There have been various that have been identified and we have been working on. And now, as far as the switching technology, we have been conducting modeling, characterization, development of new fabrication processes, and benchmarking of the different technologies. Having said that, in this slide, you see the switching technologies that we have identified, different types, membrations and PCMs, microfluid, CMOS and wafer-based switches with their advantages and challenges. In the first category, for example, we can see that they can be the membrations and PCMs to be rather miniaturized switch, non-volatile switching. But in terms of challenges, we are in a low TRL phase, and the integration is actually a bit difficult with the unit cell. For the microfluid, we can have continuous phase control, low power consumption, but challenges in the microfabrication and in the actual mechanism. This technology is still immature and an actuation mechanism has not yet been established. As far as the CMOS and wafer-based switches, This is a more mature technology, actually a family of technologies. The integration is easier. However, we need to optimize for this application low bit phase stays, so we don't have high resolution in terms of the different states responses of its unit cell, and there is a challenge related to the fabrication cost. Now, for the unit cell design, as I mentioned before, we have been working on microfluid reflective RIS on the D band. Tunability provides this technology by manipulating the movement of a liquid in space, and for passive RISs, single layer patch-based unicells, different patterns of the top layer provide the required discrete set of phases. We're talking about 1, 2, and 3-bit tunability. You can see some figures in this slide. And for the unit cell design for these transmissive RISs, there is work on the passive transmissive RISs at D band, 3 metallic layers printing on low-cost substrate with a tunability of 4 bit, and at 300 gigahertz, a wireless 3-bit reconfigurable units. We have been working also in the RIS panel overall for passive hardware. Preliminary validation of the fabrication and testing and modeling is being conducted. We're working on the manufacturing and transmissive RIS at 300 gigahertz with a directivity of 47 dBIs and a wideband 1-bit tunable reflective RIS using this technology of tightly coupled dipoles. The band spans from 50 to 150 gigahertz. This is the bottom right figure. In the middle, you see the transmissive RIS and the characterization that have been doing for the reflective RISs. Of course, there are various challenges that we have been working on the design of multi-bit phase resolution RISs in a limited physical space, as I mentioned before, and this is extremely challenging. The mitigation of the high cost for the implementation of RISs, to prove that the main KPIs for the RIS use cases can be met when realistic hardware impairments are accounted for. High power sources with advanced modulation scheme in the terahertz regime is another item within TERRAMETA. And the intrinsic phase wrapping, this is the beam spin effect that we're trying to tackle both from the hardware perspective, but mainly from the algorithmic perspective. Now going to the work related to channel modeling. So we have been working on terahertz channel measurement campaign with different RIS types. On the bottom left, you see the decided channel sounding plan for both far field and near field terahertz communications at 304 gigahertz explicitly. This will take place in the premises of University of Braunschweig, and where we will have a transmissive RIS as the transmitter, a reflective RIS as the typical RIS to do the reflection, this anomalous reflection, which we will also chain with a metal plate to see actually the impact of having a reconfigurable metasurface. The channel sounding here, you see the equipment that we're going to use, and this will be also used as a basis for development new terahertz channel models. And also we aim to design innovative algorithms for channel estimation and beamforming, novel strategies for near and far field beam management, and novel localization and JCAS schemes for systems in terahertz having RISs and ultramassive MIMO systems, mainly based on metasurface-based antennas. Now, unit cell and end-to-end RIS parameterization channel modeling, we have been working on novel multi-user near-field channel modeling approaches with holographic MIMO transceivers, unit cell wideband frequency response modeling parameterized in terms of circuital hardware parameters, extending the coupled mode theory, channel characterization from physics-inspired models, categorized mainly as scattering parameter analysis, mutual impedance modeling, and coupled dipole formalism. And we have been working also on electromagnetics consistent modeling based on the scattering matrix representation to model mutual coupling, to engineer mutual coupling, and to optimize both active and passive beamforming for downlink communication. This refers to systems that have both an RIS and multiple antennas at the transmitters and the receivers. We have been working also on estimation algorithms for ultramassive MIMO terahertz systems. We have actually designed a time domain channel estimation for extremely large MIMO terahertz communications, taking the beam squint under consideration. We have been working on channel estimation with metasurface-based receivers having very low resolution in their ADCs, reducing even further their overall complexity. And there is extensive work already on designing beam codebooks for RISs, near-field hierarchical beam management, near-field dynamic codebook for directional beamforming using metasurface-based transmitters, and also neural net-based inspired schemes for training to have fast beam alignment and beam focusing when we're talking about near-field algorithms. Beamforming strategies for ultramassive MIMO that I mentioned before. You see another bunch of works, hybrid ultramassive MIMO beamforming with dynamic metasurface antennas, low complexity fully digital beamforming transceivers added by transmissive RIS stacked, the one after the other, metasurface based receiver, as I mentioned before, with low bit resolution ADCs, as well as RIS-enabled and access point-free simultaneous radio and localization and mapping schemes, joint 3D and 6D hybrid RIS localization. This is the hybrid RIS that can simultaneously reflect and drive certain portion of the impinging signal in the baseband through a dedicated reception RF change to perform certain estimation tasks, and duplex metasurface-based transceivers for ISAC. Various planned work on the protocol for cascade channel estimation, hardware limitations to be considered on channel estimation algorithms, the inclusion of RISs to backhaul links, the sharing of RISs for multiple access points, non-line of sight localization and sensing, interference management with the aid of RISs, RF mapping with receiving a hybrid RISs, and also we're working a lot on the potential of RISs with respect to wireless activity monitoring and many others. In terms of proof of concept activities, which is a dedicated work package, we're working on 3 different directions to develop a simulation about the target activities, which will be based on the Simone simulator that University of Braunschweig is actually having, and the idea is to extend it to incorporate all these RISs, all these form of RISs and their realistic hardware behavior, lab-based demonstration to testing of the integrated TERRAMETA devices and the RIS under ideal condition to represent the best possible performance of the hardware produced within the project. And of course, the use case demonstrator, where I said before, we have 2 actually targets. The one is an outdoor at BT facilities, and the other also is in a real factory at Dell, where we have sketched already what to do. Here you see the robot. Here you see the Dell server, where the robot and both the server, we're going to have a baseband unit by intracom connected with a transmissive RIS, a reflective RIS within the air to do this real-time data transmission, high data rate links with metasurfaces. This is my last slide, referring to standardization. So TERRAMETA has been quite active in contributing to 2 standardization groups. The IEEE 802.11, which is specific on terahertz, as well as the Hexa-X-II on terahertz. And we have already 2 contributions in this specific IEEE group, plus 1 that happened a couple of days before. Ongoing opportunities within this year that we are considering. Already 5 contributions to the Hexa-X-II terahertz, the identification of use cases for THz communication and systems, and we're also targeting the specific working items within this terahertz group, but also various partners within TERRAMETA are very actively participating in the Hexa-X-II RIS. We have already prepared a contribution related to the RIS response element that we have been fabricating for those terahertz frequencies, and many of us have been actually founding members of this new ISG on ISAC, where we have been participating. We have started participating in various working items related to the technology. So thanks for your time.